The next part of the project covers several applied machine learning tasks across different datasets. Each task involves data description, pre-processing data, model planning, model building, and reporting the results. Third part demonstrates a regression workflow, pre-processing, pipeline design, and model evaluation on the abalone dataset. In this project, the goal was to predict abalone age using physical measurements. The dataset has 9 attributes, 8 features, and 1 target, that is rings, which can be used to predict the age of the abalone using the formula rings plus 1.5. First, starting with the pre-processing of the dataset. In this dataset, one column, sex, was categorical, so it was one hot encoded. Next, no missing values were present. Third, all numeric fields were standardized using standard scalar. Column transformer and a pipeline were used to ensure consistent transforms during training and prediction. Third step was model planning. In this, I selected linear regression because this is a continuous target problem. Linear regression models are fast, interpretable, and provide coefficients that reveal feature influence. The pipeline combined one hot encoding, scaling, and a linear regression estimator. Using a pipeline prevented data leakage and ensured identical pre-processing during cross-validation and prediction. Next, moving on to the results part. I split my dataset into two parts. 67% of the data was used for training the model and 33% was used for testing the model. With this split, R-square value was found to be 0.5356, which indicates that model was able to explain 54% of the variance. Further, 10-fold cross-validation produced NMSE, that is negative mean squared error, corresponding to an RMSE corresponding to about 2.22 rings, that is 2.22 years of age uncertainty on an average. If we talk about model interpretation, I observed extremely large coefficients of some features, which indicates multi-collinearity among predictors. This instability suggests the value of regularization or switching to tree-based models to capture the non-linearities. Further, this model was validated on two hypothetical records. One record of a larger abalone predicted age to be around 13 years, and second record corresponding to smaller dimensions predicted the age to be 7 years. Considering RMSE, these predictions fall within reasonable intervals and illustrated the model's practical utility. So this was about the third part of the project, which involved using a linear regression model to predict the age of abalones. Hypothetical data provided appropriate results, which showed that this model was good for this dataset, although improvements might be possible with advanced regression. Now, next, moving on to the fourth part of the project. This involves a classification task using census data. This section covers predicting whether an individual's income exceeds $50,000 using US Census data. First, talking about the dataset. This dataset has nearly 50,000 records and 15 attributes. Predictors include age, education level, occupation, number of hours worked, capital gain, capital loss, and few others. And the main target variable is income. As I said, the primary objective of this dataset, of this task, is to predict whether an individual's income exceeds $50,000 or not. Next, moving on to the pre-processing of the dataset. This dataset went through a lot of pre-processing steps. First one, dropping FNL WGT column. This column was dropped because it was just a sensor specific attribute. Next, replaced question mark values with NA. Third, strip the white space in all the string columns. Next, converted numeric columns using pandas method to underscore numeric. Next, the target variable was encoded as, if the salary is more than 50K, then it was encoded as 1, and if it's less than or equal to 50K, then it was encoded as 0. All the categorical features like employment type, education, marital, occupation, all these categorical features were one hand quote encoded, and all the missing values were imputed with the mode. Similarly, all the numeric features, in those numeric values where they were missing, they were imputed with the median value. After pre-processing, next step was the model selection. For this, logistic regression was chosen for the binary classification because it's interpretable, it's efficient for large data sets, and it provides coefficients which are helpful for explaining the relationships between features and income probability. Next, building the model. The full pre-processing and classifier were combined in a single pipeline. This guaranteed that imputation and scaling are learned not only in training data, but are learned only on training data, and they also prevent leakage. Cross-validation and evaluation were performed on the complete pipeline. Next, talking about the results. As before, the dataset was split into 67 and 33 ratio, 67% being used for training and 33% being used for testing the data. This split resulted in overall accuracy of 84.96%. Deeper analysis shows a stronger class imbalance. This model achieves very high recall, 0.96 for the majority class, that is where the salary is less than or equal to 50K, but there was a poor recall, just 0.27 for the minority data, that is greater than 50K. This indicates bias towards predicting the majority class. 10-fold cross-validation produced mean accuracy of 0.851 with standard deviation 0.007, confirming stable behavior across folds. The model generalizes reliably but underperforms on the high income class. Next, this model was tested on 2 hypothetical profiles. This model misclassified a clearly high income profile as less than or equal to 50K. That is a false negative, demonstrating the current model threshold and class bias issues. The second record, the low income profile, was correctly predicted. This highlights the need to tune for recall on the minority class if identifying high income individuals as the priority. So, in summary, logistic regression provides a stable and explainable baseline with strong accuracy, but class imbalance limits its ability to detect the minority class. Next, moving on to the part 5th of the project, which is an unsupervised clustering project using the car evaluation dataset. Here, I used k-means to discover natural groupings of the car based on 6 ordinal features: price, maintenance, doors, passengers, luggage, and safety. The evaluation column exists in the data, but this was not used for training so that we could validate cluster interpretability afterward. In EDA, I verified that the features were ordinal and consistent. There were no major missing values. The evaluation label distributions supported selecting 4 clusters corresponding to the categories unaccording, ACC, good and very good. Talking about pre-processing step, because these features are ordered categorical values, I applied ordinal mappings to preserve the ranks, that is very high being 4, high to 3 and so on. After mapping, I scaled all the features with standard scaler to make the distances meaningful for k-means. Next, model development. K-means was run with n clusters, that is number of clusters being 4 and random state being specified so as to have consistent results. 4 clusters align with the datasets evaluation categories and produce interpretable centroids that can be reverse mapped to the original labels. Next results. Cluster 0 captured higher quality cars, that is higher maintenance level, higher passengers and luggage and better safety. That is aligning with good or very good. Cluster 2 captured small budget cars with low passenger capacity and lower safety, aligning with the ACC or un-ACC category. We validated cluster assignments against the reserved evaluation models and found good alignment. Sample records placed the high-end car in cluster 0 and the budget car in cluster 2 as expected. So we can say the k-means cluster method provided meaningful interpretable groupings that aligned with the real-world categories. The key to success was correct ordinal mapping and scaling. This clustering could be used for segmentation, pricing strategies, or recommendations.